Welcome to the deep dive. This is where we take sources you're curious about and we extract the knowledge you need pretty fast.
Think of it as your shortcut to getting genuinely well-informed.
And often finding a few surprises along the way.
Hello, the learner. We get it. You want to gain knowledge efficiently, thoroughly, see different angles, get those aha
But
moments.
without the information overload.
Exactly. That's what we aim for here.
So today we're diving into some really interesting material you sent over. It's all about design algorithms, optimization.
Was it a lecture transcript and a briefing doc summarizing the main ideas?
And our mission really is to explore how this algorithmic thinking, how it applies to design challenges.
Yeah.
In fields like computational design, architecture, that sort of thing.
Yeah, and we'll be looking closely at two main ways of thinking algorithmically: bottom-up and top-down problem solving.
Okay.
And understanding the difference, well, it can actually really shift how you approach design. It offers some powerful new perspectives.
All right, let's unpack that. These two approaches, bottom up and top down. What exactly are we talking about here in the design context?
Okay, so bottom up. With that approach, you start with the basics, the fundamental building blocks,
Like algorithms themselves?
right? Core algorithm concepts, data structures, like grid algorithms, maybe dynamic programming, graph theory principles. You start there, and you build up from those elements to tackle the bigger design problems.
So it's like you have your toolkit of basic techniques and you figure out how to combine them for a specific design job.
Precisely. Now, top down, that flips it.
Okay.
You start with the design problem itself, the actual challenge.
Right. The lecture had examples, calculating floor area ratio.
Yeah, or analyzing sunlight in a room, maximizing rental income, even just making text more visible on a map, those kinds of things.
So you define the problem clearly first.
And then you figure out which algorithms or methods you need to actually solve it.
That makes intuitive sense for design. I think the speaker even said, in architectural problems, the problems we have are all top-down, really.
That's a really key point. Design usually starts with a need, a question, a requirement.
Not with a list of algorithms.
Exactly. So the top-down way fits that workflow better. You focus on the what, the design challenge, before the how, the algorithm.
And that lets the designer maybe explore solutions more creatively instead of being limited by the algorithms they already know.
Absolutely. It shifts the focus from the tools to the actual problem.
Could we maybe use an analogy just to make the difference super clear?
Sure. Think about cooking.
Okay.
A bottom-up approach is like looking in your pantry. You see flour, eggs, sugar, and thinking, okay, what can I make with these?
Starting with the ingredients.
Right. Top-down is deciding, I want to bake a chocolate cake, and then figuring out the specific ingredients and steps you need for that cake.
Got it. Start with the parts versus start with the finish thing. Okay, let's dig into some of those top-down examples. The text color contrast one sounded interesting. How does that work?
Yeah, it's a great example because it seems simple, right? Just make text readable on a map.
But the background colors change all over the place.
Exactly. The lecturer mentioned, I think, California and Hawaii being hard to read on their map example. A single text color just won't work everywhere.
So the top-down question is just, how do we make it visible against all these different backgrounds?
Precisely. And that simple question opens the door to different algorithmic solutions.
Like what?
Well, the lecturer mentioned looking at color difference metrics, maybe cosine similarity between colors.
Cosine similarity. How does that apply to color?
It's basically a mathematical way to see how alike two colors are in their direction in a color space, ignoring brightness for a moment.
Okay.
Or you could use distance metrics, how far apart are the colors mathematically, or even algorithmically finding complementary colors.
Wow. So even a visual choice like text color can have some pretty complex math running underneath.
Absolutely. It's all driven by that top-down need for contrast.
What about the CAD snapping? That's a user experience thing everyone knows.
It really is, and it's another perfect top-down example. The user needs objects to snap easily to nearby points.
You just expect it to work.
You do. But behind that simple expectation, there's an algorithm figuring things out.
So what's the logic? What's the top-down process there?
Well, the system has to find the closest point to your cursor, but only within a certain small distance, a tolerance.
Okay.
If it finds a point within that range when you click or move something, then it triggers the snap. It aligns your object to that point automatically.
Seems straightforward enough, but the lecture mentioned optimization, especially with lots of points.
Ah, yes. Because what if your drawing has, thousands, maybe millions of points?
searching every single one would take forever.
Exactly. It would grind the software to a halt.
Oh,
So you optimize. You use techniques like partitioning the search space, dividing the drawing area into smaller chunks or regions. The algorithm then only needs to search for points in the immediate area around your cursor.
much faster. Like searching a small part of the beach instead of the whole thing.
Pretty much. So the user gets that smooth top-down experience, easy snapping, thanks to some clever algorithmic optimization underneath.
Smart. Okay, and the last top-down example was geometric constraints, like scaling something without messing up its proportions.
Yeah, precisely. The user's top-down need is, I want to resize this, but keep the aspect ratio locked.
Right.
And the software makes that happen through simultaneous calculations.
Yeah.
You drag one corner, and the algorithm instantly figures out how the other dimensions need to change to maintain those proportions.
So one user action triggers a whole chain of calculations behind the scenes.
Yep. The speaker called it a geometry's top-down problem. The user's goal drives the algorithmic solution.
This really clarifies how top-down works. It starts with the user need, the design goal.
Okay, let's switch gears slightly. Deterministic versus stochastic algorithms. They sound pretty different. They are, fundamentally. A deterministic algorithm. Give it the same input, you get the exact same output. Every single time.
No randomness.
None at all.
The parking garage example was deterministic, right?
Yeah.
Maximize cars in a fixed space. Why is that?
Because you're looking for the one single best answer. The layout that fits the absolute maximum number of cars.
Okay.
For a problem like that with clear constraints, you can usually devise an algorithm that finds that single optimal solution predictably.
And the lecture mentioned other deterministic areas, like,
Geometric calculations, generally.
yeah.
Environmental analysis, sunlight, water flow. Building energy simulations.
Ah.
Things based on, predictable physics or math.
Right, same starting point should give the same result. So stochastic is where the randomness comes in.
Exactly. Stochastic algorithms have some element of chance built in.
Meaning?
Meaning even with the same starting input, you might get different outputs each time you run it.
The example was placing columns for a roof with agents.
Yeah, an agent-based simulation.
Right.
You have constraints like avoid these void areas, stay within the boundary, but then you might have randomized agents. Maybe they represent different load patterns or people moving through the space. Something unpredictable.
And that randomness affects the final column placement.
It can, yes. So the goal isn't necessarily finding one perfect solution because of that randomness.
It's more about finding a generally good solution, an optimal one that works well across different random scenarios.
Precisely. You often run these stochastic simulations many times, look at the range of outcomes, and find a robust solution.
Interesting. And this ties into the idea of an objective function.
Absolutely crucial concept. The objective function or cost function, loss function in machine learning, it's how you mathematically define what you're trying to optimize.
What you want to maximize or minimize.
Exactly. Maximize parking spaces, minimize material waste, maximize rental income, minimize energy use, whatever the goal is. It gives the algorithm a target.
So without that clear objective function, the algorithm doesn't know what good means.
Pretty much. And linked to that are metrics.
The evaluation criteria.
Yes, how you actually measure success. The lecture used that analogy of comparing sports. You need objective metrics to say which is harder. Same in design. You need clear metrics to see how well your algorithm is doing against your objective.
Right.
The speaker really hit it home. Defining what to minimize and what to maximize is ultimately the design process.
That frames it perfectly. It's not just about generating options, but having a solid way to judge them. And I guess optimizing often involves trade-offs.
Almost always. Very rarely can you maximize everything you want.
Like the parking garage example, again, maybe maximizing spots means the driving lanes get uncomfortably narrow.
Exactly. Improving one metric might hurt another. The objective function and your metrics help you see, quantify, and make decisions about those trade-offs.
Which leads us neatly into parametric design and the Pareto front. How do they fit in?
Well, parametric design is about using parameters, variables, to define a whole range of possible designs, the design space, as the lecture called it.
So instead of one fixed design, you have a system that can generate lots of variations just by tweaking the inputs.
That's the idea. Now, imagine you have multiple goals, multiple objectives.
Like the window example. Maximize light, but also maximize privacy.
Right. Often you can't get the absolute best of both. If you make the window huge for light, privacy suffers. If you make it tiny for privacy, you lose light.
The trade-off.
Exactly. And the Pareto front helps visualize this. It's the boundary line on a graph showing all the optimal solutions.
Optimal in what sense?
In the sense that you can't improve one objective, like light, without making another objective, like privacy, worse. They're the best compromises available.
So any solution on the Pareto front is efficient. You can't do better on both counts simultaneously.
Correct. Solutions inside the boundary are inefficient. You can improve both light and privacy by moving towards the front. The speaker said, those that are maximized are creating the boundary outside.
Got it. So it helps designers see the range of best possible trade-offs and choose based on their priorities. It's a way to navigate those competing goals.
Precisely. It brings mathematical clarity to those multi-objective decisions.
Okay, we've covered these big approaches. What about the underlying nuts and bolts? The foundational stuff designers should maybe know.
Right, the building blocks. The lecture touched on core data structures, ways to organize data efficiently.
Right.
Arrays, hash tables or dictionaries, stacks, queues, linked lists, trees, graphs. Each is good for different things.
For example.
Well, say you're managing tons of design assets like textures or components. A hash table lets you look them up really quickly using a name or keyword. Very efficient retrieval.
Makes sense. And basic algorithms.
Fundamentals like sorting, putting things in order.
Mm-hmm.
Think insertion sort, bubble sort. Useful for organizing data. Maybe optimizing material cuts to reduce waste.
Okay.
And searching algorithms. Linear search, binary search, finding specific items in your data. And things like graph traversal DFS, BFS.
Depth first search. Breadth first search.
Yeah. Really useful for analyzing connections, like paths in a building layout or network relationships. BFS, for instance, could find the shortest path from a central point.
So is the idea that designers need to be expert coders for all these?
Not necessarily. It's more about understanding how they work conceptually. What are their strengths? When might you use one versus another in a design context?
Understanding the logic, not just the code.
Exactly. That lets you apply them creatively.
Okay, putting it all together, we have these approaches: deterministic, stochastic, objectives, metrics, foundations. How does this crystallize into a computational design process, and where else do we see it applied?
The big idea is framing design as quantifiable, defining steps, metrics, constraints, making it more data-driven, less purely intuitive.
So for you, the learner, seeing design through this lens could open up new ways to tackle problems.
Definitely. Regardless of your specific field, it's a way of thinking.
The lecture had some diverse real-world examples.
Yeah, quite a few. The brick facade design was interesting, angling bricks based on light and visibility needs.
Right. Or the memorial design, optimizing name placement for visibility using algorithms, maybe stochastic ones. Measuring visibility was the key metric there. Then there was material modeling, simulating swelling or cracking based on parameters like moisture. And even interactive point clustering on maps, grouping points dynamically as you zoom.
Wow, from bricks to maps to materials, it really shows the breadth. And there was advice on implementation.
Yes, basically. Start simple, build solid low-level algorithms first, then combine them logically to build up more complex systems.
A layered modular approach
Yep.
makes sense for handling complexity.
Absolutely.
Okay, this has been a fantastic exploration. Let's just quickly recap the main takeaways.
Sounds good. So we hit the difference between bottom-up and top-down thinking in design, why top-down often fits better.
Starting with the problem.
Exactly. Then deterministic versus stochastic algorithms, predictable versus incorporating randomness.
And the huge importance of objective functions in metrics. You have to define success to optimize for it. Critically important. And finally, the Pareto front for visualizing those inevitable trade-offs in multi-objective design.
And the core message seems to be that viewing design algorithmically focusing on data, process, evaluation gives you really powerful new tools.
It absolutely does. It enhances creativity. It doesn't replace it.
So here's a final thought for you, the learner, to mull over.
Yeah, think about a design problem you know well. Could be work, could be personal.
How could you frame that problem using a top-down algorithmic approach, or maybe even bottom-up?
And crucially, what specific metrics could you use to actually measure how good different solutions are?
Definitely something to chew on. Thank you so much for joining us for this deep dive.
Our pleasure.
And if you, the learner, have other topics or sources you want us to tackle, please send them our way. We're always ready for the next exploration.